Hello, everybody. Welcome to this webinar for the Centre for Data Science. This is a distinguished visitors webinar. We're delighted to have with us today Dr. Sandra Johnson. Sandra has a long history at QUT and long involvement with QUT as a student and as a researcher and as a long-term collaborator. So Sandra will start with just a very brief description of where she is now and what she's and her profession, and then she's going to talk about her current work in this webinar series. Before we start the webinar, though, I would like to pay my respects to the Yagara and Turrbal people here at QUT, and pay my respects to their elders, past, present, and emerging. The lands here at QUT have always been places of learning, and we're proud to be able to continue that tradition. So I'll hand over now to Sandra, and welcome, Sandra.
Thank you very much for the introduction, Kerrie. So just a little bit about myself. I'm currently working at a ConsenSys Software company in the R&D department. So I was excited to be able to use what I was doing previously at QUT, which is research applying Bayesian network technology to some of the research there. And currently, I'm looking more in the sort of incentive systems analysis, which is a very exciting and new area for me. But today, I would like to talk to you about work that I've done in the past. And I'll just share my screen and make sure that you're all able to see that. I'd just like to say thank you to QUT Data Science Centre for the opportunity to talk to you about the process of modelling stateless Ethereum, which is work that I've undertaken at ConsenSys and also in collaboration with my co-authors here, including Kerrie. So this work has been published as a conference paper in the Electronic Proceedings for Theoretical Computer Science. And we presented this work at the 5th workshop on models for formal analysis of real systems in March this year. So just for some context, to understand what I mean by Ethereum state, well, the Ethereum world state consists of Ethereum accounts and balances, deployed smart contracts, which really is just sort of a program code, and the program language of choice is called Solidity, and also the associated storage with those programs. So new accounts are continually being added, as you can imagine, and also new smart contracts are being deployed. And in a blockchain, nothing is ever deleted. So by design, the state size of Ethereum keeps growing ad infinitum, which leads to unbounded state growth. And the repercussions of this is that we have impacts on network performance due to slower transaction processing, because having a larger state means longer lookup times for the transactions and slower block verification, because changes to the state needs to be, each node has got to recompute it. So it's recomputed by the client to build the new state trie and compute a new root hash. So that's pretty computationally intensive. And this, coupled with a need for higher computing resources to run and maintain an Ethereum node, will lead to a less diverse ecosystem of Ethereum nodes, which is really not desirable. Now, Vitalik Buterin, and anyone involved with or heard of Ethereum would know him as the founder of Ethereum. He recognized these potential issues back in 2017 when he introduced the concept of stateless Ethereum. And that is really just a protocol transformation based on state transition functions. The key component of this proposal is what's called a block witness. And a block witness would contain a set of Merkle branches that are authenticated against the state root and contains all the data required to execute the transactions in that particular block. So in other words, it provides you all the information you need to prove the validity of the block and to perform the state transition. But now, the important question to ask is, what effect will these witnesses have on the ecosystem? What are the potential consequences of passing additional data packets around the network? How large will they be? Can the size be reduced? So the strategy, the approach we used was Bayesian networks. And for anyone not familiar with Bayesian network modeling, I will just give you a quick overview. So what is a BN? Well, people often point out that a Bayesian network is a probabilistic graphical model. So let's just take a step back and get context of where BNs fit within the whole framework of probabilistic graphical models. So with graphical models, we can roughly be broken into those that have got directed edges between the variables in the graph and those that have undirected edges, such as Markov networks, or perhaps better known as Markov random fields. Then we also have hybrid graphical models. And by hybrid, I mean in the sense that they contain both directed and undirected edges, as we see in chain graphs. Now, Bayesian networks fall under the directed graphical models, and they have directed links between the variables or nodes in the graph, and it's also acyclic. So in other words, we cannot contain any loops. Now, a couple of the specializations of BNs are dynamic BNs and OBNs. And the latter approach, object-oriented Bayesian networks, is the approach that we used for the network I'm going to be talking about today. So who is Bayes? Clearly with Bayesian networks, Bayes being featured in the name refers to Reverend Thomas Bayes. And I just thought it'd be fun to take a step back in history a bit and look at who Thomas Bayes actually was. So he was born in 1702. He was the eldest son of Anne and Joshua Bayes. And his father, Joshua Bayes, was one of the first 6 publicly ordained nonconformist ministers in England. And therefore, Thomas was educated privately, which was really the norm for children of nonconformist ministers. And I think that stood him in good stead in a way, because there was speculation that he was tutored by eminent French mathematician Abraham de Moivre, who fled France when there's persecution of Protestants. And de Moivre also wrote a book on probability theory, which is called The Doctrine of Chances, a method of calculating the probabilities of events in play. And he was reportedly also friends with Edmund Halley and Isaac Newton. So pretty interesting people to know. One pretty weird fact that I think is weird is that Abraham de Moivre correctly calculated the date of his death. But, to me, when you read it about it, I think he sort of contributed to, to make that happen. Anyway, Thomas Bayes became an ordained minister, starting his ministry by helping his father at the Presbyterian meeting house in Leather Lane in London, before he moved to a Presbyterian meeting house, Mount Sion Chapel in Royal Tunbridge Wells, Kent in England. Now, Richard Price, a friend of Reverend Thomas Bayes, published his work after Bayes died in 1761. So he published his work in 1763, which was basically 2 years after he died, after Thomas Bayes died, and he represented it to the Royal Society of London. And it was called An Essay Towards Solving a Problem in the Doctrine of Chances. And this is also probably more commonly known by people as a method to solve a problem of inverse probabilities. Now, this equation here is a very well-known Bayes theorem. And the central idea of Bayes' theorem is that we start with a prior belief about the possibility of a hypothesis or event, which is represented here by the probability of A. And then we revise our belief to take new evidence, which is referred to as B here in the equation, which is extra informational data that we take into account. And this data or this additional information may either confirm or contradict our hypothesis. So we therefore look at the probability that we observe this data, given that the event or the hypothesis is true. And so that's known as the likelihood. We divide this by the probability of the data B to produce the posterior belief, which is the probability of A given B. And this simple equation provides us with a very intuitive way of dealing with probabilities. And we can reframe questions of chance, update probabilities with data or evidence, and so essentially sort of switching a question around. So far we've seen that a BN is a graphical probabilistic model. And actually this graphical nature assists us with stakeholder engagement, which is particularly helpful in Bayesian networks where experts help to guide the model structure and if we need to elicit probabilities. It is a directed acyclic graph, as I mentioned. But what makes a BN Bayesian? Well, behind each of these nodes you can see there in the diagram, we've got a conditional probability table. So essentially, a BayeSnet is just a joint probability distribution made up of a set of conditional probabilities. And once you have that, you can then think of it in reverse. What is the probability of the outcome given the rest, and the probability of the other nodes given the outcome of interest? Now, with BNs, there are two important statistical properties that makes probability propagation through the model more tractable. And these two are the Markov property and a D-separation. So let's first look at the Markov property. So the Markov assumption is that if we know the present, then the past has no influence on the future. And related to this concept of a Markov, the Markov assumption is the concept of a Markov blanket. Now, a node's Markov blanket consists of its parents, its children, and its children's parents. And it can be shown that a node is conditionally independent of all other nodes, given the values for the nodes in its Markov blanket. So just to quickly illustrate that, if we look at node C2, its parents are C3, C4, and C6. It has only one child, which is the outcome of interest. And then we need to also look at the children's other parents, which is C7. So these 6 nodes form the Markov blanket for C2. Now, the other important BN property is the concept of directional separation or D-separation. And with directional separation, if 2 nodes are D-separated given a third node, then A and B are conditionally independent, given C, for example, or X and Y are D-separated given Z. And then X is conditionally independent of Y given Z. So using these 2 important properties, it makes probability propagation through the model far more tractable. So the classic way of computing a joint probability distribution, you can see there in the first equation. And this can be greatly simplified to what is commonly known as the BN chain rule. So here the joint probability is a product of the probabilities of the nodes given only their parents. So that makes it a lot more tractable, as I said. Now, object-oriented Bayesian networks are a specialization of BNs, and it allows a much more sort of modular approach to modeling that's particularly suited to complex systems, because you sort of get rid of a whole lot of the clutter because you sort of effectively hide it when you look at it. So in an OOBN, we have private nodes, input nodes, and output nodes. So some strange feedback there. The nodes you can see in the diagram with just a single line oval shape are the private nodes. For example, a property size is a private node. And the beauty of this is that we can change these nodes without impacting the rest of the model, other than through the defined interface that's there. So the interface, as is indicated there, consists of the input and the output nodes. And we can think of an input node really just as a placeholder in a model. And an output node means that it's visible to other OOBNs. So in a way, the input node would sort of be a placeholder for an output node from another model. So for example, if you look in this diagram, then short-term economic drivers, pasture growth and income are placeholders for these nodes that would have been modeled as output nodes in another OOBN model. We can also add a complete OOBN to another model, as is shown here with those ones with their like rounded edge rectangles. And these OOBN models are known as instance nodes, and they can either be a complete submodel or a network fragment. So if you have something that's repeated several times, so you can just then use this instance node a few times. And we ended up choosing Hugen Expert software to build the model, specifically because it has good OOBN capability. And in actual fact, Bayesian networks have been used in a wide variety of disciplines, such as the ones listed here. And I've got references for them at the end of the slides, if anyone's interested to look at them. So why did we decide to model Stateless Ethereum as a BN model? Well, to answer this question, let's have a quick look at the BN modeling characteristics. So they are a useful tool to model complex systems, and Ethereum certainly is a pretty complex environment. It's statistically rigorous approach, regardless of whether there's plenty of data, whether there are plenty of data or we have data paucity. They're able to use diverse data sources for a model, such as empirical data, expert knowledge, grey literature, academic research, output from experiments, and the Ethereum community has a wealth of knowledge about the Ethereum ecosystem. So being able to also leverage expert knowledge is really valuable in this particular modeling exercise. The visual nature of BNs means that the assumptions are explicitly represented in the graphical structure of the BN, which is helpful in the expert elicitation process that will be required for stateless, both for the structural, both structurally and for the probabilities. And we explicitly capture uncertainty through the joint probability distributions. And it enables us to reason under uncertainty and run sort of what-if scenarios by entering evidence into the model. So for example, to represent a particular scenario and propagate that through the network. So BNs is a iterative approach, and it can learn from new research and data as they become available. So although we may model in a causal way, the direction of inference can be different to the direction of modeling. And it, for example, it can give us insights into knock-on effects and facilitates decision-making under uncertainty, for example, to find the best policy from a set of possible policies. So finally, with Stateless Ethereum, we have changes that are being introduced into a stable, well-functioning ecosystem. So a BN seems to be an ideal way to look at this problem. Now here is just a high-level overview of the view of the 4 OBN models that make up the Stateless Ethereum model that we built. So on the right, you can, the submodels are expanded. So you can see these interfaces I mentioned between the models that will govern the information flow between them. And we will look in detail at the quantification of one of the submodels, the Ethereum network model, because it's a pretty good example of the variety of techniques we used in the model to quantify it. So first of all, if we look at the top one, the block producer, basically by block producer, we mean by it's either sort of a miner that produces blocks, or it's the other type of nodes that will receive the block, validate it, and add it to their copy of the network. So this node has got two states, miners and what we termed semi-stateless nodes. And by semi-stateless, I mean that in stateless Ethereum, the nodes can have varying degrees of statelessness. So it's up to them to decide how much state they keep updated, because there could be particular parts of the state that they're not interested in, and it's not necessary for them to keep that current. But anyway, if we have a full node, it will have zero statelessness because it will have all of the information. So that's what currently people refer to in Ethereum as you've got full nodes, for example. And then if a new node joins this stateless Ethereum network, it will have complete statelessness, so sort of 100% statelessness. So all the other nodes will therefore have like varying degrees of statelessness. And then it seemed a fairly simple question to ask, well, what proportion of the Ethereum nodes are miners? But surprisingly, it was not an easy question to answer, because it's not always easy to find out exactly who the miners are. But we are able to calculate an upper estimate using empirical data. And then we consulted with experts to adjust those probabilities, and they provided us with both point and interval estimates. So now if we move along and look at the node bandwidth. To quantify node bandwidth, we combined empirical data extracted from a website called ethernodes.org. And we consulted with experts to then adjust those probabilities, especially with respect to how these proportions would vary for block producers versus the other nodes. But also because contributions to Ethernodes is voluntary, so not all Ethereum nodes are actually represented here. The node states we have for this node are high, medium, and low. So business and hosting nodes have been deemed to have high bandwidth. College and residential nodes have got medium. We're assigned to have medium bandwidth, and all other categories were deemed to have low bandwidth. Now, the conditional probability tables were calculated as weighted averages, guided by the uncertainty of the expert elicited values. Then we look at node location. Now, according to ethernodes.org, at the time that we did the web scraping, there were about 86 countries reported as running Ethereum nodes. And we grouped these into 86 countries, into the 5 regions that you can see listed here. So Europe, North America, China, rest of Asia, and the rest of the world. Just for interest, this is a visualization of those 5 regions where Ethereum nodes were running that contributed data to that website, ethernodes.org. So to calculate the conditional probabilities, we provided a baseline calculated from ethernodes.org, and then we consulted with the experts. And we employed various elicitation techniques to suit each expert. So whatever they felt more comfortable with, some preferred ranking locations, and others were happy to provide actual probability estimates. Then peer location was pretty challenging actually to quantify, because we did not have access to any empirical data. And we know that many factors play a role in the choice of the peers that you have. So the peers that are connected to you, and then you receive and send out block notifications. So it can be the choices for peers to a node. Those sort of factors like connectivity and trust play a role. For example, miners probably have direct connection with other miners to propagate new blocks quickly. However, the experts deemed that the overarching consideration would be the location of the peer and whether or not it is a miner. And they agreed that peer locations are actually would sort of closely mirror those of the node that they connected to. And lastly, we look at network latency. Now, there are actually several ways to model network latency, but the main contributing factor is geographical location of a node and its peers. So using GNU GNU ping data from Wonder Network, which reports on ping times between cities. We then had to organize the data. So this was in a lot more sort of granular level, because we got city data, whereas ethernodes.org, we had country data. So we organized the data and we grouped these into regions as well to match the locations that and the node locations from that we had in the previous slide. And then we calculated inverse variance weighted means to take the between and within city and region variations into account. And then we grouped the times into bins. So if it was less than 30 seconds, it was deemed to be low, between 30 and 100 medium, and more than 100 as high. Now that the OBN model is fully quantified, we can run it as a standalone model. And this then gives us the marginal probabilities. We can now also ask what if questions. So for example, we may be interested to know if we have a node running in Europe, how is that likely to affect network latency? So to represent the scenario, we need to set the node location in the model to Europe. So we do this, we just, if you have the model there, you just double click on Europe, and that will set the probability of being in Europe to 100%, and it highlights that state in red, as you can see in the diagram. And then by propagating this belief through the model, we observe the expected changes to the network latency probability distribution. Now, if we look at the next two submodels, which is the block creation submodel and the witness creation submodel, which are quite closely related. So block creation is a very complex process, but this simplified structure is able to capture the key factors. There might be a few factors here that you'll find might be helpful if I explain that. So block gas limit means, so you have, it limits the gas expenditure per block to keep block propagation and processing time low. So all the transactions in a block will use some what they call gas to run. And this then sets the limit as to how much gas can be used within that block. Then block gas used is then just the actual gas, the total gas that was used by all transactions in that block. The other interesting one I'd like to point out is difficulty. So Ethereum dynamically adjusts the difficulty level of cryptographic graphs, cryptographic puzzles in the mining algorithm to keep the block creation time within a preset range. So it really is effectively the difficulty for miners to find a block and be rewarded for generating a valid block. Then for the witness creation submodel, you can see there are three input nodes that were all quantified in the block creation model to the left. And it has one private node and one output node. So for the witness creation, we implemented the witness specification as it was at the time of modeling in a form of the Ethereum client called Hyperledger Besu. And then we generated the witnesses according to what was deemed to be the specification for witnesses at the time. And we generated witnesses for 26,595 blocks. And then data from these blocks and the witness implementation were then used for us so we could learn the conditional probabilities. We also had an exercise of running 6 structure learning algorithms that are available within Hugen. And this exercise suggested some minor changes. For example, a directed link between block gas limit and difficulty in the block creation model was sort of supported by most of them, which we didn't have in the model before. So we included that, especially because it made logical sense as well. So then we used the data to learn the conditional probabilities. So now we can run these two submodels and obtain their marginal probability distributions. So you can see that here for the probability distributions for the different nodes. So again, we could run some various scenarios through these models in a similar way to what we did for the Ethereum network model. So the next submodel I'd like to mention is the block propagation submodel. And that has a total of 5 input nodes from 3 other submodels. And the 2 output nodes, uncle rate and node keeps up with the head of the chain. So again, if we run that, we get the marginal probabilities. So for this particular submodel, we used a variety of data sources and techniques to quantify it. So for the block propagation time, we collected information from 3 different sources. So there were 2 websites, one called ethstats.io and the other called ethstats.net. Since then, one of them has been deprecated. And we also used block propagation times between geographically diverse nodes from a month-long experiment conducted by Silva et al., which is in the references at the end, number 18, where they collected Ethereum network data. So we combined information from these 3 data sources for the prior probabilities, and the extent to which node latency and bandwidth have an effect on block propagation time were elicited from experts. Now, I'd like to point out again just a couple of interesting factors here. One is called uncle rate. So to explain what an uncle is, it's either called uncle or OMA. So when there are 2 or more miners and they produce a valid block at the same time, and they both attempt to add it to the chain, only one will be added to the canonical chain. And the other block doesn't just get discarded, but it's known as an uncle or an OMA block. And there's incentives there for the next block to include these OMA blocks as part of their valid block. So the CPT for this was learned from empirical data. The node status, where node can either be up to date, in other words, it's tracking the head of the chain. It could be busy syncing to the head of the chain, or it could be offline. And actually, when it is offline, it's pretty difficult to know whether it's having difficulty keeping up to date with the head of the chain, whether it's been decommissioned, whether it's having technical difficulties, or due to some other reason. For nodes keep up with the head of the chain, we relied entirely on expert judgment for the conditional probability entries. So we now have an almost complete quantification of the model. And if we look at this, you can see that for the final outcome, we've got 2 input nodes, 2 nodes going into to that last final outcome. And uncle rate and node keeps up with the head of the chain are the 2 factors informing the Ethereum ecosystem health. And the reason they were chosen was because if you have a very high uncle rate, it adversely affects transactional throughput through the ecosystem. And when there's difficulty synchronizing to the network, that would be indicative that there are network-related issues. So the only remaining task then was to quantify the Ethereum ecosystem node using expert judgment. We are now able to run the combined network, and as you can see from here, the high probability was healthy, a healthy state at 56%. In other words, health of the Ethereum ecosystem with a basic stateless implementation. In other words, we did not include any compression of witnesses, is expected to be healthy. And as suggested by one of the reviewers of our conference paper, it would be interesting to run the model without generating witnesses. And so we did that. And there's an absolute increase in the probability of a healthy ecosystem of 4% and a relative percentage gain of 7% for the ecosystem being healthy. To the right, you can see differences in probability distribution of other model variables, such as block and witness processing time, and node keeps up with the head of the chain. There are several caveats attached to the results from this model. It's important to remember that quantification was done only with a subset of Ethereum mainnet data. We used only 26,595 blocks. Moreover, it predates Ethereum Improvement Proposal, or EIP as they're commonly known in Ethereum, community, so ERP 1559, which has seen increased block sizes, and the maximum block size is now twice as large as it was at the time of the modeling. We also did not implement any compression technique when we generated the witnesses, because nothing was available at the time of implementation. Or rather, there were several ideas. We're still a work in progress. There was no sort of agreed way to go. The current proposal, when I last checked, was to use Virtual tries to reduce the witness size. Lastly, the presence of expert knowledge can introduce bias into a model. So for those reasons, for the reasons I just mentioned, the probability of the final outcome, the Ethereum ecosystem being healthy, should not be interpreted as an exact result, but rather as a reference point for assessing changes in probability when we explore the effect that various scenarios have on the predicted health of the ecosystem. We actually ran some scenarios through the complete model. For example, we can ask the question for a semi-stateless node and a very large witness, how would that affect the ability of a node to keep up with the head of the chain? So we decided to represent this question in two ways. First of all, we entered evidence to say the witness sizes were all in the second largest bin of witness sizes. And then the worst case scenario that the witnesses were in the largest bin size. And entering this evidence into the model indicates that these scenarios are fortunately unexpected to be pretty unlikely. The probability of these scenarios is 23.7% for the first and 5.9% for the latter. So they resulted in a relative decrease of 11 and 17% in the probability that the ecosystem will be healthy. So then we looked at doing some sensitivity analysis. So in Bayesian modeling software, such as Hugen, we've got the ability to perform different types of sensitivity analysis on the model, so we can assess the robustness of the model and the results of the model. As we know, the results of any model is sensitive to the underlying assumptions. In sensitivity analysis, we refer to, when I talk about a parameter, it means it's an entry in the conditional probability table. So we performed one-way parameter sensitivity analysis under different evidence scenarios, investigating the impact of probability parameter variations on the probability of the hypothesis that the ecosystem is healthy. It is in fact also possible to do two-way parameter sensitivity analysis. We found that the parameter with the highest value of the sensitivity function at the initial parameter assessment, in other words, the one with the highest impact, was the probability that the ecosystem is healthy, given that the node is able to keep up with the head of the chain, and it is a high uncle rate, which we denote by T in the slide there. And the sensitivity function, you can see, having entered no evidence, and the sensitivity value for this evaluated to a value of less than 1, and a value of less than 1 means that the posterior probability of the hypothesis is relatively insensitive to variations in the parameter assessment. We then performed some one-way parameter sensitivity analysis under two other evidence scenarios and investigated the impact of probability parameter variations on the probability of the hypothesis that the ecosystem is healthy. So the scenario here in the slide is denoted by epsilon. And we call this scenario, the first one of them we call the base scenario, which had low witness creation times and low block propagation times. So those are very favorable conditions. And T denotes the Bayesian parameter, which is the probability that the node is offline, given block propagation time is low and it's not a block producer. In other words, it's not a minor. For this base case, the sensitivity function is given by equation 1. Then the other evidence scenario we selected, and we called the most severe scenario. Here, the evidence has the largest business size, and it's a semi-stateless node. And for the same parameter as the previous one that I just talked about in the base scenario, the sensitivity function here is given by equation 2. And again, the sensitivity value was less than 1 in all the 3 scenarios. So no evidence, base and most severe. And worst case sort of in all 3 of those scenarios as well, the base case, worst case, and no evidence, the sensitivity function was linear due to the structure of the evidence. So we then assessed the robustness of the results with respect to variations in evidence. And these are the parameters that produce the largest variations in the posterior probability of the hypothesis that the ecosystem will remain healthy for the various scenarios. All other variables produce a much smaller variation in the probability of the hypothesis. So although this is not always the case, in this instance, the sensitivity analysis we performed to assess the robustness of the model did not reveal any unexpected model behavior, which would have required a revision of the model structure. So in summary, object-oriented Bayesian networks add a modular approach to the strengths of Bayesian network modeling, which was very well suited to modeling a complex system such as Stateless Ethereum. And the ability of Bayesian networks to include diverse data sources such as empirical data, model output, and expert knowledge provides us with a view of the proposed system that takes into account all available information at the present time. However, it is important to acknowledge that the presence of expert knowledge can introduce bias into the model, and conducting sensitivity analysis and model verification are particularly helpful in identifying and mitigating this bias. Identifying variables and parameters with high impact on the results need to really be given special attention. So BN modeling is typically an iterative process, and what I presented here today is the initial model. And it could be updated to include developments since its implementation, such as the EIP 1559 that I mentioned to you, where the maximum block size is now doubled, and also the latest witness reduction techniques, or also to evaluate the effects of different types of witness reduction techniques on the overall model. So some of the key challenges in this project were that the degree of data coverage was variable, and this introduces measurement errors, which are compounded by elicited probabilities and interpolation, which introduces bias into the model. So although the main aim of Stateless Ethereum remains unchanged, the ways in which this is achieved it evolves sometimes rapidly over time. And that can make it quite challenging to model. And while we were busy, things did change. But it makes it fun and it makes it challenging. So we actually have an online model of this model, which is hosted currently on the Hugin demo website. Now, I would just like to say that apart from my main collaborators, this project has benefited from generous time and expertise given by a huge number of people, ranging from relatively casual conversations about aspects of the topic or model to dedicated time to participate in elicitation exercises and reviews. So before we move to questions, I would just like to draw your attention to the upcoming conference of the Australasian Bayesian Network Modelling Society, or ABNMS, because that's a bit of a mouthful. And this will be held at the University of Sydney on November the 16th and 17th. And typically accompanying these conferences, we have tutorial sessions that range from beginner to advanced topics. So if you're interested in BN modeling, please visit the Society's website and also check out our YouTube channel that has recordings of presentations and webinars. The Society launched this webinar series only last year, and it's also continuing on this year. And the call for papers will open up in July. And I'm happy to take questions because I haven't monitored the chat. I'll stop sharing.
Thanks very much, Sandra. That was excellent. If anybody has any questions, please put them in the chat, and we can discuss them. But I'll start off, Sandra. I mean, it's just such an interesting area, the Ethereum and this whole area. And obviously there are different platforms. So there's Ethereum, there's other platforms as well. So how well does this model sort of translate to other setups?
Well, that's an interesting question because if we look, for example, at Bitcoin, they don't have the concept of smart contracts running on them. But there are several other networks that would be similar. But so I suppose with all of them, it would be looking at these different submodels in a way and see which ones would translate more easily to others. And the other interesting thing is that Ethereum is looking at what they call the merge, which will be a different way of producing blocks where we move away from proof of work to proof of stake. So one potential project we have is to look at how we can adapt this existing model to represent a proof of stake type of model. So that is something we're considering at the moment. Okay,
interesting. You talked at the end about it's always easy to pick up on the challenges and the issues, but you talked about this issue of bringing together different data sources and sort of almost scraps of information. They're not scraps, but they're important in their own right, but they're sort of parts of the full story. The nice thing about the Bayesian network approach is that it's sort of like bringing in that quantitative information or being able to quantify diverse information sources and bring it into a common framework. But then you also talked about when these, you have this sort of parts of information, that also has some measurement error or some uncertainty associated with it. So it's based on samples or based on, has some uncertainty. So how do you see, in general with Bayesian networks, and so sort of a question at the moment, uncertainty in those probabilistic statements or in those conditional probability tables sort of being able to propagate through the network? And in your experience, because you've built many of these networks in different contexts, how much of an issue do you think that is?
As I said, I think one of the key things we can do is if we look at sensitivity analysis, and we use also model verification and the different strategies that people use, by running through different scenarios and doing, first of all, just like desktop checking and then more in-depth checking. And I think especially with object-oriented BNs, it's possible to look at the individual models in isolation as well as part of the bigger model. So certainly that is an issue. And, if it's highlighted that some of them are contributing, have got a particularly high impact, we should really be looking at whether this is, what we need to do. So the thing is also in this particular instance, the caveat that we think is particularly important is not to take these as an exact result, but rather we're looking at what are these differences. If we look at different scenarios, what are the differences? Because the danger always is when you come up with a number is that people take that as to be, this is what you want. But so we were trying to just emphasize as well that this is a reference point and we can look at how things vary with that. So I think just having a lot of eyes as well on it. And if, people are doing additional experiments, there's new research happening, and we can also mitigate some of these by just updating things as we do with, in any Bayesian approach with new data so that the data speaks more than the other opinions that we have from experts.
Okay. It sounds like 100 questions, and I'm really happy if other people have questions, please put them in the chat. But Sandra, how has this been sort of received by the company, by ConsenSys, and then also by the community, the Ethereum community, this kind of modelling?
Yeah, that's a good question, Kerrie. So certainly varying reception. So within the Theorem community, this sort of approach is not very commonplace. It tends to be more game theoretic and simulation approaches. And yet, as I said, there've been excitement as well in the fact that looking at this holistic approach rather than what they tend to do often is run individual experiments about parts of it. So even though they understand, implications of different bits, they found it interesting that it's possible to look at all of these at the same time. Because obviously the thing I like about beings is you don't need to keep all of the things in your head. You just put them all down and then see how each one sort of connects up with the others. So I was particularly pleased as well that, as I said, I was contacted to say, could we look at this for proof of stake? So that was some positive feedback there that people did, but that was within ConsenSys R&D, where another team thought that this would be a useful approach. So yes, it's had some good feedback. As I said, I think there was more hesitation when I proposed it more, but afterwards I think people have come on board a bit more.
Yeah, it's interesting, isn't it? Because sometimes people can't sort of, it's the same for all of us, so it's hard to imagine something that you haven't seen, and once you get to see something in this area, then you start to be able to imagine what it could look like and what the extensions could be, and and try to figure out how to overcome some of the challenges or the limitations and so on. But it's interesting. It must be interesting being sort of trailblazer, bringing this this kind of modelling and this kind of quantitative assessment to this area.
Yeah, it's been quite fun. It's been fun, I must say.
Is it a big community in terms of the sort of the analytics community and the modelling community?
Yeah. Well, I mean, the Ethereum community itself is pretty large and very active. There's a lot of research happening with a lot of different companies, and the Ethereum Foundation itself drives a lot of the research. And we also try and collaborate with them on a lot of the work that we're doing. So especially with Stateless Ethereum, we were in close contact with the Ethereum Foundation people, as well as they've got things like Discord, Ethereum Discord. So you've got an opportunity there as well to interact with others in the community.
Okay. Well, we're going to have to close given the time. But also, Sandra, I know that you've had as I said, a long history in building Bayesian networks and modelling in a range of areas. From airports through to conservation and different kinds of conservation. So I'm guessing the kinds of approaches that you've talked about here, the kind of model is very transferable to these other areas. And I'm guessing if people would like to talk to you about those other applications, then you'd be open to those conversations.
I'd be delighted, yes.
Okay, all right, thank you. Well, thank you very much for being our distinguished visitor and for giving this seminar. I'm hoping that the world will change and we can have face-to-face meetings very openly, and people feel comfortable about that, and then we can have these kinds of seminars, and we can invite you back then for we can have some face-to-face interaction. But in the meantime, I really appreciate you coming on to give this seminar online. The seminar's been recorded, so we know that there will be people who told me they couldn't make it to this time slot, but we'll be wanting to review this afterwards. And so I really appreciate your time, your expertise, your great communication of this topic, and lots of bits that we didn't understand and didn't know beforehand. And you've really brought it to life for us. So thank you very much for that.
Thank you so much, Kerrie. And I really enjoyed the opportunity to talk to all of you, and I hope you enjoyed it, the talk. Thanks.
Okay, all right. Thank you. And thanks, everybody. And thanks to Becky and Tim for
thanks,
the
Becky.
background organisation.
Thanks all.
Okay. All right.
Bye.
Bye for now.